Isn't it remarkable how we can grasp a sense of distance, even when numbers seem to stretch beyond our immediate experience? It's like imagining a familiar place, maybe your favorite chair, and then trying to picture it further and further away. It seems simple, doesn't it? But try to hold that image, that feeling of distance as we begin to contemplate truly vast scales. We talked a little about light years, that peculiar unit that measures not time but distance using the speed of light. And light, as you know, is incredibly fast. But even at that speed, the distances we encounter when looking beyond our solar system are staggering. Let's gently revisit that idea of something being far away. Think about the sun. It feels quite far sometimes, doesn't it? It's a source of warmth, of light, of life, but it also casts long shadows, creates a sense of space. Now imagine our sun, this enormous ball of burning gas, suddenly shrunk down to the size of a tiny marble, a marble sitting on a table in front of you. Now picture all the planets in our solar system, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, also shrunk down to proportional sizes, orbiting that marble sun. They would still be incredibly small, wouldn't they? So small, you might have trouble even seeing them clearly. And beyond Neptune, stretching out into the darkness, lie even more distant objects, icy worlds, dwarf planets, and comets, each a tiny speck in the immensity of space. That's a glimpse of our own cosmic neighborhood. But what about other neighborhoods? Our Milky Way galaxy, the swirling island of stars we call home, is just one of billions, perhaps trillions, of galaxies scattered throughout the observable universe. And among those countless galaxies, there are others that capture our attention, that whisper stories of vastness and potential. One such galaxy is Andromeda. It's our galactic neighbor, a colossal spiral structure much like our own Milky Way. Think of it like this. Imagine standing in a vast forest, surrounded by towering trees. Each tree represents a star, shining brightly in the darkness. Our solar system is like a tiny wildflower, hidden amongst the undergrowth of our Milky Way forest. And Andromeda is like another forest, equally immense, visible in the distance on a clear night. It appears as a faint, fuzzy patch of light, a smudge in the sky. But don't let its faintness fool you. It's a universe unto itself, filled with hundreds of billions of stars, swirling clouds of gas and dust, and untold mysteries waiting to be uncovered. Andromeda's diameter, defining size. So, how do we begin to grasp the size of something so distant, so immense? We've talked about distance, about light years, but now we want to consider its diameter, its breadth, its span. It's helpful to start with something familiar, something we can easily visualize. Let's think about Earth again. We know Earth is roughly 12,742 kilometers in diameter. That's a big number, certainly, but it's a number we can relate to. We know the distance you can drive in a day, and that gives us a sense of scale. Now imagine a line stretching across the middle of Earth from one horizon to the opposite horizon. That line represents Earth's diameter. Now let's picture that line extended and extended and extended until it reaches the Sun. And then even further past the orbit of Mars, past the asteroid belt, past Jupiter, and even past Saturn. Keep stretching that line. It's a bit dizzying, isn't it? Trying to visualize such a vastness. Andromeda is significantly larger than our own Milky Way. Scientists estimate Andromeda's diameter to be around 220,000 light-years. That's a much larger number than 12,742 kilometers. A dramatically larger number. Let's try to make that a little more comprehensible. Remember how we shrunk our solar system down to a table? Now imagine Andromeda's disk, its main body, stretched out to encompass our entire solar system, and then stretched out again, and again, and again. Imagine that disk extending outwards to include not just the planets, but all the distant icy bodies, the Kuiper belt, and even the Oort cloud, that vast theoretical sphere of icy debris that surrounds our solar system. Andromeda's disk still wouldn't reach its edge. It's like trying to imagine the circumference of an ocean when you've only ever seen a small puddle. Think about a large flowing river. You see a small section of it, perhaps a bend in the river or a calm pool of water. But you know that river extends far beyond what you can see, winding its way through valleys and plains, eventually emptying into a vast ocean. Andromeda is similar. We only see a small portion of it, a tiny glimpse of its immense structure. But it extends far beyond our vision, a sprawling dynamic system of stars and gas. To really get a sense of Andromeda's size, let's consider this. If you were standing on a planet within Andromeda, and you could somehow see the Milky Way galaxy, it would appear as another faint fuzzy patch of light in the sky, not unlike how we see Andromeda from Earth. It would be a humbling perspective, wouldn't it? To realize that our own galaxy, our cosmic home, is just one of countless others, each a vast and complex system of stars and planets. It's a perspective that tends to quiet the mind, doesn't it? It invites a sense of wonder, a feeling of connection to something far greater than ourselves. Now, Andromeda's diameter isn't a perfectly precise number, of course. Measurements of such vast distances are always subject to some degree of uncertainty. It's like trying to measure the height of a distant mountain range. The further away you are, the more difficult it is to get an accurate reading. And there's also the fact that galaxies aren't perfectly flat, perfectly circular disks. They are dynamic, evolving structures with swirling arms and bulges and halos of gas. So, Andromeda's diameter isn't a single fixed value. It's more of a range, a best estimate based on our current observations and understanding. But even with all those uncertainties, the sheer scale of Andromeda remains awe-inspiring. It's a reminder that the universe is far more vast, far more complex, and far more beautiful than we can possibly imagine. And isn't that a comforting thought? That there's always more to discover, more to learn, more to marvel at. That there's always more to discover, more to learn, more to marvel at. It's a feeling that invites us to look a little closer, isn't it? To try and grasp, even in a small way, the immensity of it all. And when we look at Andromeda and we consider its vastness, a natural question arises, doesn't it? A question that whispers in the quiet spaces of our minds. How does it compare to our own galaxy, the Milky Way? It's a lovely question, a simple question, really. But the answer, like so much in the universe, is layered and complex. Imagine, if you will, two enormous cakes, each baked to a different recipe, each decorated with its own unique artistry. Andromeda and the Milky Way are like those cakes, aren't they? They're both swirling masses of stars, gas and dust, bound together by the relentless pull of gravity. They both have spiral shapes, arms that wind outward from a central bulge. But if you were to stand before them side by side, you might notice some subtle differences. And those differences, even though they seem small, reveal a great deal about their history, their evolution, their place in the grand cosmic tapestry. Andromeda, you see, is generally considered to be larger than the Milky Way. Its diameter is estimated to be somewhere between 200,000 and 260,000 light-years. Think of a light-year, just for a moment. It's the distance that light travels in 1 year, traveling at an incredible speed. It's hard to truly comprehend, isn't it? The sheer distance involved. The Milky Way, on the other hand, is thought to be a bit smaller, with a diameter somewhere between 100,000 and 180,000 light years. So Andromeda stretches out a bit further, doesn't it? Imagine those two cakes again. Andromeda would be the slightly larger cake, taking up a bit more space on the table. But that's a surface-level comparison, isn't it? Like saying one cake has more frosting than the other. It doesn't tell the whole story, because the number of stars each galaxy contains is also quite different. Andromeda is believed to harbor somewhere between 1 trillion and 1.5 trillion stars. That's a staggering number, isn't it? Almost beyond comprehension. The Milky Way, by comparison, is estimated to have between 100 billion and 400 billion stars. So Andromeda not only stretches out farther, but it also contains significantly more stars. Think about the night sky, don't you? Even with all the stars we can see with our eyes, even with the most powerful telescopes, it's clear that there's so much more out there, isn't it? A vast hidden universe waiting to be explored. But size and star count aren't the only differences, are they? The composition of the stars within each galaxy can also vary. For example, Andromeda appears to have a higher proportion of older stars compared to the Milky Way. Older stars are generally redder, cooler, and less massive than younger stars. They've simply had more time to burn through their fuel, haven't they? Like a candle slowly flickering down. The Milky Way, on the other hand, has a greater abundance of younger, bluer stars, particularly in its spiral arms. Younger stars are often formed in regions of intense star formation, where gas and dust collapse under their own gravity. It's a process of constant creation and destruction, isn't it? Stars being born, living out their lives, and then eventually dying, scattering their elements back into the interstellar medium where they can be recycled into new stars. And what about the central regions of these galaxies? Andromeda has a supermassive black hole at its center, just like the Milky Way does. These black holes are incredibly dense objects with gravitational pulls so strong that nothing, not even light, can escape. They play a crucial role in the evolution of galaxies, influencing the motion of stars and gas in their vicinity. The supermassive black hole at the center of Andromeda is estimated to be about 100 million times the mass of our Sun. The one at the center of the Milky Way, Sagittarius A Flies, is a bit smaller, about 4 million times the mass of our Sun. Still unimaginably large, of course. Imagine a grain of sand, and then imagine something 100 million times more massive than that. It's a mind-bending thought, isn't it? And as these two galaxies continue to evolve, they are destined to collide. Billions of years from now, the Milky Way and Andromeda will slowly begin to merge, drawn together by their mutual gravitational attraction. It's a slow dance, a cosmic ballet unfolding over an incomprehensibly long timescale. The collision won't be a sudden, catastrophic event, though. Instead, it will be a gradual process, with stars and gas swirling around each other, eventually settling into a new, larger galaxy. Think about two streams of water flowing into each other. They don't simply crash together violently. They blend and mix, they become a single, larger stream. It's a beautiful image, isn't it? The idea that these two vast galaxies, each containing billions of stars, will eventually come together to form something new. And as they merge, the night sky will look very different. The familiar constellations we see today will be unrecognizable. New stars will be born, new planetary systems will form, and the universe will continue to evolve. It's a humbling thought, isn't it? To realize that our place in the universe is not permanent. That galaxies collide, stars are born and die, and the very fabric of the cosmos is constantly changing. And yet, within that constant change, there is also a sense of order, a sense of beauty, a sense of wonder. Isn't it remarkable? The way these galaxies, so different in some ways, are also so similar. They both spiral, they both contain billions of stars. They both harbor supermassive black holes. They are both expressions of the same fundamental laws of physics, playing out on a cosmic scale. And even though Andromeda is larger than the Milky Way and contains more stars, it doesn't make either one inherently better, does it? They are simply different, each unique in its own way, each contributing to the richness and diversity of the universe. It's like comparing a rose to a sunflower, isn't it? One is larger, one is more colorful, but both are beautiful in their own right. And both play a vital role in the ecosystem. The universe is full of surprises, isn't it? Full of things that challenge our assumptions, that expand our understanding, that inspire our sense of wonder. And as we continue to explore the cosmos, we will undoubtedly discover even more astonishing facts about galaxies like Andromeda and the Milky Way. Perhaps we'll find that there are even larger galaxies out there, galaxies containing even more stars. Perhaps we'll discover new types of galaxies that we haven't even imagined yet. The possibilities are endless, aren't they? And the journey of discovery is just beginning. It's a comforting thought, isn't it? And the journey of discovery is just beginning. Isn't that a lovely feeling, this sense of infinite possibility? It's easy to get caught up in the sheer size of these things, the vast distances, the countless stars, and it's wonderful to do so, truly. But sometimes it's helpful to think about things in a slightly different way, to consider something beyond just what we can see. We've talked about how Andromeda and the Milky Way appear to us, the light we receive from them. That light tells us so much, doesn't it? About their shapes, their colors, the types of stars they contain. But light is just one piece of the puzzle, isn't it? Think about it this way. Imagine you're sitting in a field of wildflowers. You can see the bright petals, the vibrant colors, the delicate shapes of each flower. That's like looking at Andromeda's light. It's what immediately draws your attention. But you also know that there's more to each flower than just its petals, don't you? There's a stem, roots, leaves, all working together, unseen, to support that beautiful bloom. And the weight of the flower itself, the substance, isn't entirely captured in the brightness of its colors, is it? There's a density, a presence, a mass that influences how it feels in your hand, how it interacts with the wind. Andromeda's mass, beyond just light. It's a slightly different way of thinking about these galaxies, isn't it? We focus so much on the light, it's understandable, really. Light is how we perceive the universe at a distance. But what about the weight of a galaxy? What does it even mean to talk about the mass of something so vast? Well, think of it this way. Imagine you're trying to understand how strong a river is. You could look at how quickly the water is flowing, the color of the water, the plants growing along its banks. That's like observing the light from a galaxy. But to really understand the river's strength, you'd also want to know how much water it carries, isn't it? You'd want to know its volume, its density. That's similar to what we're trying to do with Andromeda's mass. It's not just about how brightly it shines, but how much stuff it contains. And the stuff isn't just stars, you know. It's also gas, dust, dark matter, things we can't directly see with light. Dark matter, that mysterious substance that makes up a significant portion of the universe's mass. It doesn't interact with light in the same way ordinary matter does, doesn't it? It's invisible, elusive. But we know it's there because of its gravitational effects. And Andromeda's mass includes a whole lot of dark matter, doesn't it? Measuring the mass of a galaxy like Andromeda is a tricky business, isn't it? We can't just put it on a scale, obviously. Instead, we rely on the effects of its gravity. Think about how planets orbit a star. Star's mass dictates how quickly the planets move, doesn't it? The more massive the star, the faster the planet's orbit. We can use the same principle to measure the mass of a galaxy. We look at how stars and gas clouds move within the galaxy. And from their speed, we can infer how much mass is pulling on them. It's like observing the dance of the wildflowers in the field, isn't it? The strength of the wind, the weight of the raindrops. These things influence how the flowers sway. By observing their movements, you can learn something about the forces acting upon them. Andromeda's mass is estimated to be significantly greater than the Milky Way's, isn't it? Roughly about 1.5 times more massive, they say. But those numbers are always subject to change as we refine our measurements, don't they? It's a bit like trying to weigh a cloud. It's constantly shifting, changing shape. And the more we learn about dark matter, the more challenging it becomes to accurately determine a galaxy's mass, doesn't it? Because dark matter is so pervasive, so influential. Its effects are felt throughout the galaxy. It subtly alters the movements of stars and gas clouds, making it more difficult to isolate the contributions of ordinary matter. It's like trying to understand the rhythm of a dance when some of the dancers are invisible, influencing the movements of the others, isn't it? You can see the dancers, but you can't see the forces guiding them. This difference in mass, Andromeda being more massive than the Milky Way, doesn't necessarily mean one is better or more important, does it? It simply means they've evolved differently, accumulated different amounts of matter over billions of years. Perhaps Andromeda has been more efficient at attracting gas and dust from its surroundings, doesn't it? Perhaps it has experienced more galactic mergers, incorporating smaller galaxies into its own structure. Think back to the rose and sunflower. One might be larger, more substantial than the other. But does that make it inherently superior? No, doesn't it? They are simply different expressions of the same fundamental principles of nature. Andromeda's mass gives it a stronger gravitational pull, doesn't it? It influences the movement of stars and gas clouds within its boundaries. It affects the distribution of dark matter in its halo. It's like a more powerful magnet, attracting and holding more material around it. But it also means that Andromeda's gravitational influence extends further into space, doesn't it? It's a cosmic ripple, affecting the motions of galaxies far beyond its visible boundaries. Isn't that a remarkable thought? That that something so distant can have such a profound effect on the universe around it? It highlights the interconnectedness of everything, doesn't it? How even the most seemingly remote objects are linked by the invisible threads of gravity. And as the Milky Way and Andromeda continue their slow, inexorable dance towards each other, their gravitational influence will become even more pronounced, won't it? That will distort each other's shapes, disrupt the orbits of their stars, and ultimately merge into a single, larger galaxy. A grand cosmic collision unfolding over billions of years. And even then, the mass of the combined galaxy will be just a tiny fraction of the total mass of the universe, isn't it? It's humbling, isn't it? To realize how vast and immense the cosmos truly is. To understand that even the largest galaxies are but tiny specks in a sea of stars and galaxies. It's a reminder that our perspective is limited, isn't it? That there's so much more to learn, so much more to discover. Yet within that vastness, there is also beauty, order, and a sense of wonder. Andromeda's mass, like so many other cosmic mysteries, invites us to ponder, to explore, to question. Isn't that a privilege? Andromeda's mass, like so many other cosmic mysteries, invites us to ponder, to explore, to question. Isn't that a privilege? It draws our gaze outward, doesn't it? Towards something far larger than ourselves, far grander than anything we can truly grasp in a single moment. But the mass itself, this enormous quantity of stuff, it's not just about how much there is. It's also about what that mass is made of, isn't it? And when we think about that, we begin to think about the stars themselves. Imagine, if you will, a field of wildflowers, a vast, sprawling meadow filled with blooms of every imaginable color. Each flower, in its own way, is beautiful. But the beauty isn't just in the individual flower, is it? It's in the collective beauty of the field, the sheer number of blossoms, the way they sway in the breeze, the way the light catches their petals. And each flower is made of something, isn't it? Petals, stems, roots, soil, all different materials contributing to the whole. Galaxies are, in some ways, like that field of wildflowers. Each star is like an individual flower, shining with its own unique light. And the galaxy, the entire swirling structure, is like the entire field. So we've talked about Andromeda's mass, this gravitational influence rippling outwards. But how many of these flowers, these stars, are actually in Andromeda? That's a question that continues to intrigue astronomers, doesn't it? It's not a simple count, of course. It's not like counting apples in a basket. Stars are incredibly far apart, aren't they? The distances between stars are truly staggering. Think about it. Even within our own Milky Way galaxy, the nearest star to our Sun, Proxima Centauri, is over 4 light-years away. A light-year, remember, is the distance light travels in a year. And light travels incredibly fast. So even the closest star is an enormous distance. Now imagine that distance multiplied countless times, because that's the scale we're dealing with when we consider a galaxy like Andromeda. It's a little like trying to count grains of sand on a beach, isn't it? You start, and you realize it's simply too vast a task. Early estimates, based on observing Andromeda's brightness and assuming certain things about the types of stars present, suggested that it contained around 1 trillion stars. 1 trillion? That's a 1 followed by 12 zeros. A truly mind-boggling number, isn't it? It's hard to truly grasp, isn't it? It's a number so large that it's almost meaningless. But newer observations using more sophisticated telescopes and techniques are giving us revised estimates. And those estimates are even higher. We now believe that Andromeda might contain up to 1.5 trillion stars. That's 1.5 trillion. Imagine adding another 0.5 trillion flowers to that meadow. The field stretches even further, the beauty becomes even more overwhelming, doesn't it? But even these numbers, staggering as they are still estimates. They're based on assumptions and models. We can't see every star in Andromeda, you see. Many are obscured by dust and gas, hidden from our view. And some are simply too faint to be detected, even with the most powerful telescopes. It's like trying to count the number of trees in a dense forest, isn't it? You can see some, but there are countless others hidden behind the canopy. So, the actual number of stars in Andromeda could be even higher than we currently estimate. It's a humbling thought, isn't it? To realize how much we still don't know. And not only that, but these stars aren't all the same, are they? They aren't all like our own sun. They come in a huge variety of sizes, temperatures, and ages. Some are massive, brilliant blue giants burning through their fuel incredibly quickly. Others are small, faint red dwarfs, burning slowly and steadily for billions of years. Think of the wildflowers again, remember? You have towering sunflowers, delicate violets, vibrant poppies, all different, all contributing to the beauty of the field. And just as there are different types of flowers, there are different types of stars, isn't there? These different types of stars, astronomers call them stellar populations. The older stars tend to be redder, cooler, and smaller. They've had time to burn through the heavier elements and settled into a quieter existence. The younger stars, on the other hand, tend to be bluer, hotter, and larger. They're still in the early stages of their lives, burning bright and furiously. And Andromeda, like our own Milky Way, has both old and young stars. It has a complex history, hasn't it? A history of star formation, of stellar evolution, of galactic mergers. And these different stellar populations tell us a story about that history. It's a story written in the light of distant stars. And as we analyze that light, as we study the characteristics of these stellar populations, we can learn more about the history of Andromeda, about how it formed, how it evolved, and how it came to be the magnificent galaxy that we see today. Isn't it fascinating to think that light, traveling for millions or even billions of years, can carry such a wealth of information? It's a cosmic message, isn't it? A whisper from the past telling us about the universe and our place within it. And even with these new, higher estimates of the number of stars, something still feels incomplete, doesn't it? It's not just about the number of stars, is it? It's about the matter those stars are made of. What elements are present? How were they distributed throughout the galaxy? And those questions, those deeper inquiries, lead us to consider something even more fundamental. Something even more mysterious, dark matter. Something even more mysterious, dark matter. It feels almost silly to say it, doesn't it? To invoke a name like dark matter when we're talking about something we can't directly see, something we can only infer from its effects. It's like feeling a gentle breeze rustling the leaves of a tree and knowing there's wind even though you can't see the wind itself. You feel its presence, its influence. And that's essentially what we're doing with dark matter. We observe its gravitational effects on visible matter, on stars, on gas clouds, on entire galaxies. we see how galaxies rotate faster than they should, given the amount of visible matter present. Think of a carousel, does it not? If the horses are spinning around and you know how many horses there are and how strong the motor is, you can predict how fast they should be moving. But what if they're spinning faster? What if the carousel is defying your expectations? Wouldn't that suggest there's something else contributing to the rotation, something invisible, something providing extra pull? That something else is what we suspect is dark matter. It's not that our understanding of gravity is necessarily wrong, you see. Rather, it's that there's more to the universe's mass than we can account for with the stuff we can see and interact with. It's as if there's an extra ingredient in the cosmic recipe that we haven't identified yet. And in the case of Andromeda, the discrepancy is substantial. The visible matter, the stars, the gas, the dust, simply doesn't have enough gravitational pull to explain the observed rotation speeds of the galaxy. It's a puzzle, isn't it? A beautiful, challenging puzzle. And this puzzle isn't unique to Andromeda. We observe it in countless other galaxies throughout the universe. It's a universal phenomenon. So if we accept for the sake of argument that dark matter exists, and the evidence is compelling, what does that mean for Andromeda's structure? What form does this invisible matter take? While scientists believe that galaxies are embedded within vast, extended halos of dark matter. Imagine, if you will, a snow globe. You have the swirling snow inside, representing the visible stars and gas. And now imagine a larger, invisible sphere surrounding the snow globe, providing the structural support, the gravitational scaffolding. That's analogous to a dark matter halo. Dark matter halo, Andromeda's invisible crown. It's a poetic image, isn't it? A crown of darkness, enveloping the galaxy. Unseen but profoundly influential. This halo isn't uniformly distributed, of course. It's denser closer to the galaxy's center and gradually tapers off with distance. Think of ripples in a pond, doesn't it? The ripples are strongest where the stone hits the water and gradually diminish as they spread outward. The dark matter halo behaves in a similar way, its density decreasing with distance from Andromeda's core. Now here's a particularly intriguing aspect. The dark matter halo isn't just a static, unchanging structure. It's dynamic, evolving over time. Galaxies like Andromeda grow through mergers and interactions with smaller galaxies. And each time a galaxy merges, its dark matter halo becomes part of Andromeda's larger halo. It's like adding layers to an onion, isn't it? Each layer represents a past merger event, a cosmic collision that reshaped Andromeda's structure. And these mergers leave their mark on the dark matter halo, creating complex substructures, smaller clumps of dark matter within the larger halo. These substructures are incredibly faint, incredibly difficult to detect directly, but their gravitational influence can still be observed. They act like little gravitational ripples, subtly affecting the motion of stars and gas in the galaxy. It's almost as if the galaxy is whispering secrets about its past, encoded in the gravitational patterns of its dark matter halo. And the size of Andromeda's dark matter halo is staggering. It extends far beyond the visible boundaries of the galaxy, reaching distances of hundreds of thousands of light years. A light year, as you know, is the distance light travels in 1 year. And light is incredibly fast, isn't it? To think that Andromeda's dark matter halo stretches across such immense distances is truly mind-boggling. It highlights just how vast and interconnected the universe is. We've been talking about dark matter in terms of its gravitational influence. But what is dark matter made of? That's the million-dollar question, isn't it? We don't know. That's the frustrating but also exhilarating truth. There are many theoretical candidates, many possibilities being explored. Some scientists believe that dark matter is made up of weakly interacting massive particles, or WIMPs for short. These particles would interact very weakly with ordinary matter, making them incredibly difficult to detect. Others propose that dark matter is made up of axions, even lighter particles than WIMPs. Still others suggest that dark matter might be something entirely different. Something we haven't even conceived of yet. It's a mystery. A profound and persistent mystery. And the search for dark matter is one of the most active and exciting areas of research in astrophysics today. Think of it as a cosmic scavenger hunt, doesn't it? Scientists are meticulously searching for clues, for any trace of this elusive substance. And the fact that we don't know what dark matter is only deepens the mystery, doesn't it? It reminds us of how much we still have to learn about the universe. And it's humbling, isn't it? To realize that the vast majority of the universe is made up of something we can't directly see or understand. It's a reminder that our knowledge is always incomplete, always evolving. And that's okay, isn't it? That's part of the joy of exploration. The wonder of discovery. The universe isn't giving up its secrets easily. And that makes the quest all the more rewarding. And Andromeda's dark matter halo, this invisible crown, is a testament to the complexity and grandeur of the cosmos. It's a window into a realm beyond our current understanding. A realm that beckons us to explore, to question, to discover. It's a cosmic invitation, isn't it? To delve deeper, to learn more, to unravel the mysteries of the universe, one dark matter particle at a time. And perhaps, just perhaps, one day we'll understand the true nature of this enigmatic substance, this invisible scaffolding that holds galaxies together. Wouldn't that be something? Wouldn't that be something? To truly grasp the essence of what makes up so much of what we see and don't see out there. It's a profound thought, isn't it? And it's easy to get lost in the scale of it all, to feel a little overwhelmed by the sheer immensity of the unknown. But perhaps that's part of the beauty of it, doesn't it? That there's always something more to discover, something new to ponder. And even as we uncover these pieces of the puzzle, we realize that the puzzle itself is far larger and more complex than we initially imagined. Like peeling back the layers of an onion, doesn't it? Each layer reveals another, and another, each one adding to the depth and complexity of the whole. And in Andromeda's case, this invisible scaffolding of dark matter isn't the whole story, is it? There's also the matter that we can detect, the matter that interacts with light, the matter that we can, in a sense, see. And that's where things get even more interesting, doesn't it? Because this visible matter, the gas and dust, isn't just floating around randomly. It's actively participating in the ongoing drama of the galaxy's evolution. Imagine a cloud, a vast, sprawling cloud, drifting gently in the sky. That's kind of what we're talking about, but on a scale almost impossible to comprehend. These clouds aren't made of water vapor, of course. They're made of hydrogen and helium mostly, along with traces of other elements. And they're filled with tiny grains of dust, like microscopic specks of soot. Now, these clouds are incredibly diffuse, meaning the particles are spread out over a huge volume. Think about trying to breathe in a cloud of feathers, doesn't it? It's there, but it's so spread out that it's hard to feel its presence. It's similar to what it's like in these vast clouds of gas and dust. But even though they're diffuse, they still contain a tremendous amount of material. And this material is the fuel for star formation, isn't it? Stars, as we know, are born from the gravitational collapse of these clouds. When a region within a cloud becomes dense enough, gravity begins to pull the gas and dust inward. It's like a slow, steady trickle of water carving a path through a mountain, doesn't it? Gradually, inexorably, the material accumulates, forming a denser and denser core. As the core contracts, it heats up. And eventually, the temperature and pressure become so extreme that nuclear fusion ignites. That's when a star is born. And it's a truly spectacular event, isn't it? A sudden burst of light and energy, illuminating the surrounding space. But star formation isn't a continuous process, is it? It happens in fits and starts, in pockets of denser gas and dust. And the rate of star formation depends on a variety of factors. The density of the cloud, its temperature, its rotation, all play a role. And of course, the presence of dark matter influences things too, doesn't it? Because dark matter provides the gravitational scaffolding that helps these clouds to collapse in the first place. It's like a gentle nudge, a subtle pull, encouraging the gas and dust to come together. And just as the dark matter halo shapes the overall structure of Andromeda, these clouds of gas and dust dictate where the stars will be born. Think about a potter shaping a piece of clay, doesn't it? The potter's hands guide the clay, shaping it into a beautiful form. In a similar way, the gravitational forces within Andromeda, influenced by dark matter and the distribution of gas and dust, shape the galaxy's appearance and evolution. And it's a dynamic process, isn't it? The galaxy isn't static, it's constantly changing. New stars are born, old stars die, gas and dust are recycled. It's a cosmic dance, a continuous cycle of creation and destruction. And the gas and dust content of Andromeda isn't uniform, is it? There are regions that are rich in gas and dust, and regions that are relatively depleted. The rich regions are the birthplaces of stars, while the depleted regions are the remnants of previous generations of stars. Imagine a forest, doesn't it? Some areas are thick with trees and undergrowth, while others are more open and sparse. Similarly, Andromeda's gas and dust clouds are distributed unevenly throughout the galaxy. And this distribution is influenced by a variety of factors, including the galaxy's spiral arms. Spiral arms are regions of enhanced density within a galaxy. They're like waves propagating through the galactic disk, compressing the gas and dust into denser regions. And it's within these spiral arms that star formation is most active, isn't it? Because the denser gas and dust are more likely to collapse under gravity and form stars. But even within the spiral arms, there's a lot of variation in the gas and dust content. Some regions are much more active than others. And these variations can be caused by a variety of factors, such as the presence of supernova remnants. Supernovae are the explosive deaths of massive stars. When a massive star runs out of fuel, it collapses under its own gravity and explodes in a spectacular fashion. This explosion scatters heavy elements into the surrounding space, enriching the gas and dust. And it can also trigger new star formation, doesn't it? because the shock waves from the supernova can compress the gas and dust, creating denser regions that are more likely to collapse. It's a rather violent process, isn't it? But it's also a crucial part of the galactic cycle, because supernovae not only enrich the gas and dust with heavy elements, but they also trigger new star formation. And it's through this cycle of star birth and death that galaxies evolve over time. And Andromeda's gas and dust content tells a story, doesn't it? A story of past star formation, of supernova explosions, of the ongoing cycle of creation and destruction. It's a story written in the faint glow of hydrogen and helium, in the subtle patterns of dust. And it's a story that we're only just beginning to understand. Isn't it remarkable to think that we can decipher the history of a galaxy by studying its gas and dust? It's like reading a cosmic diary, isn't it? Each entry revealing a little more about the galaxy's past. And as we continue to observe Andromeda and other galaxies, we'll undoubtedly learn even more about their gas and dust content. And with each new discovery, we'll gain a deeper appreciation for the complexity and beauty of the universe, don't you think? It's a process of continuous learning, of constant refinement. Like trying to assemble a puzzle with missing pieces, doesn't it? We have to rely on our intuition, our reasoning, and our observations to fill in the gaps. And sometimes we have to revise our understanding of the puzzle as new pieces are found. But even with the missing pieces, the puzzle is still beautiful, isn't it? Even with the uncertainties, the mysteries, the unknowns, the universe remains a source of wonder and inspiration. And the search for understanding continues, doesn't it? And the search for understanding continues, doesn't it? It's a quiet, persistent hum in the background of our minds, isn't it? A gentle pull toward the unknown. And sometimes that search leads us to unexpected places, to things that seem, at first glance, to be outliers. Things that don't quite fit the narrative we've constructed so far. Like these beautiful, shimmering collections of stars that we find within galaxies. They're called globular clusters. Have you ever seen a photograph of one? They look like glittering jewels scattered across the darkness. Dense, spherical gatherings of hundreds of thousands, sometimes millions, of stars. Imagine, if you will, standing in a field of wildflowers. Each flower a tiny point of light. Now imagine that field, compressed into a single sphere, the density overwhelming, the light breathtaking. That's something like the visual impression of a globular cluster. And they're rather peculiar, aren't they? Because when we look at them, they tell us a story that's different. A story that seems to whisper of a time long, long ago. They're ancient remnants, you see, like echoes from the very dawn of the galaxy. Think about a forest, doesn't it? You have the towering trees, the young saplings, the undergrowth teeming with life. But you also have the fallen logs, the decaying leaves, the evidence of seasons past. Globular clusters are like those fallen logs. They're the remnants of a past era. They were formed very early in the history of galaxies, much earlier than most of the gas and dust we were just discussing. The gas and dust that bursts those magnificent new stars, well, that's a more recent phenomenon. And these clusters, they formed when the universe was younger. Simpler, perhaps? Less complex. Imagine a cake, doesn't it? You start with the basic ingredients, flour, sugar, eggs, and you bake it. Then you add layers, frosting, decorations. Globular clusters are like that original cake. Simple, basic, the foundation upon which everything else is built. And their composition, it's different too. The stars within globular clusters are generally older, redder, less massive than the stars we find in the spiral arms of a galaxy. It's as if we're looking back in time, isn't it? Seeing the galaxy in a more primordial state. And their metal content, that's a particularly interesting clue. Remember how we talked about metals in astronomy? Not like the metal in a spoon, of course. It refers to elements heavier than hydrogen and helium. These elements are forged in the hearts of stars, then scattered throughout the galaxy by supernova explosions. And the globular clusters, they have very, very little of these heavy elements. It's like finding an antique spoon, doesn't it? One made of a much purer material. One that hasn't been subjected to the refining processes of later eras. It tells you something about its origin, doesn't it? It suggests it was formed before those refining processes even began. It suggests a simpler, cleaner beginning. As we observe these clusters, we can learn about the conditions that existed in the early universe. We can glimpse the raw materials from which galaxies were assembled. It's like being an archaeologist, isn't it? Carefully excavating the layers of history, piecing together the story of a lost civilization. Except in this case, the civilization is a galaxy. And the artifacts are stars. And the excavation site is billions of light years away. It's a humbling thought, isn't it? To think that we can learn so much about the universe by studying these ancient collections of stars. They're like frozen time capsules, aren't they? Preserving a snapshot of the early universe. And Andromeda, of course, has its own share of globular clusters. Hundreds of them, orbiting the galaxy like loyal companions. Each one a tiny window into the past. And when we study them, we can compare their properties to those of globular clusters in our own Milky Way galaxy. We can look for similarities, for differences. We can try to understand how these clusters formed and evolved over time. It's the process of comparison and contrast, isn't it? Like trying to understand a family history by comparing the stories of different branches. You look for common threads, for shared experiences. You try to understand how each branch contributed to the overall family tree. And it's through these comparisons that we refine our understanding of galactic evolution. We learn more about the processes that shape galaxies over billions of years. Isn't it wonderful? To think that we can unravel these mysteries one globular cluster at a time. Each cluster offering a new piece of the puzzle. Each discovery bringing us a little closer to understanding the grand story of the universe. And sometimes, understanding isn't about finding definitive answers, is it? Sometimes, it's about appreciating the complexity, the beauty, the sheer immensity of it all. These globular clusters, they're a reminder of that, aren't they? They're a reminder that the universe is far older, far more vast, and far more mysterious than we can ever fully comprehend. And that's okay, isn't it? That's part of the wonder of it all. To stand in awe of something so grand, so profound. To acknowledge the limits of our knowledge. And to continue searching nonetheless. To continue exploring nonetheless. To continue wondering nonetheless. To continue wondering nonetheless. Isn't that the most natural inclination? It's like watching a river flow, isn't it? You don't try to force the water. You simply observe its path, its eddies, its gentle curves. You notice how it erodes the banks, how it carries sediment, how it shapes the landscape over time. And you understand that the river's journey is far more complex than it appears on the surface. It's a slow, relentless process of change. Similarly, when we study globular clusters, we're observing a snapshot in a much larger, much longer story. But what if, as we gaze out at these island universes, what if we were to notice something else? Something beyond the grand clusters themselves? Something smaller? Think for a moment about a larger tree, a mighty oak perhaps. Its branches reach out, expansive and strong. But notice too the smaller plants that cling to its trunk or nestle in its lower branches. They are not part of the oak itself, but they are inextricably linked to it. They rely on the oak for shelter, for sustenance, and the oak, in turn, might be subtly influenced by their presence. It's a delicate balance, isn't it? A relationship of dependence and influence. Galaxies, you see, can have something similar. They can have companions. Smaller galaxies that orbit around a larger dominant galaxy. These are often referred to as satellite galaxies, just as those smaller plants are satellites to the oak tree. Andromeda, that swirling island of stars we've been discussing, it's not alone in its neighborhood. It has companions. Smaller galaxies that orbit around it, bound by gravity. Imagine a larger, slower waltz. Andromeda is the lead dancer, sweeping gracefully across the floor. And around her, smaller dancers twirl and glide, following her movements, captivated by her presence. They are distinct entities with their own unique characteristics. But their orbits, their paths are dictated by Andromeda's gravitational pull. These satellite galaxies aren't as massive as Andromeda. They are, generally speaking, much less luminous. They often have different shapes and structures. Some might be irregular, lacking a clear, defined form. Others might be dwarf ellipticals, faint and diffuse, like a whisper of starlight. They're often dimmer, less complex in many ways, simpler than the grand spiral of Andromeda. It's a bit like comparing a grand cathedral to a humble chapel, isn't it? Both are places of reverence, places of beauty. But one is vast and ornate, while the other is small and intimate. And the same is true of galaxies. Andromeda's satellite galaxies offer a fascinating window into the processes of galactic evolution. They tell us about the interactions between galaxies, about how larger galaxies grow and acquire smaller companions over time. Think of it like collecting pebbles on a beach. Each pebble is unique with its own shape, size, and color. And as you gather more and more pebbles, you start to see patterns emerge. You begin to understand the forces that shaped those pebbles, the currents that carried them to the shore. Similarly, as we study Andromeda's satellite galaxies, we begin to see patterns emerge. We start to understand the processes that brought them into Andromeda's orbit. And what are some of those processes? Well, it's often a tale of gravity, of course. A smaller galaxy might wander too close to a larger galaxy. and instead of being torn apart, it becomes gravitationally bound. It's caught in Andromeda's embrace and begins to orbit around it, like a moth drawn to a flame. Sometimes these smaller galaxies were originally independent entities. They existed on their own, in their own little corners of the universe. But then, through a series of gravitational encounters, they were captured by Andromeda. Other times they might have formed from the remnants of a larger disrupted galaxy. A galactic collision, perhaps. A cosmic dance of destruction and creation. And that's something to ponder, isn't it? The idea that galaxies themselves can collide and merge, that they can be torn apart and reshaped. It's a violent, chaotic process, but it's also a fundamental part of galactic evolution. These satellite galaxies, they can also provide clues about the early universe. The very first galaxies were likely much smaller and less massive than the ones we see today. And some of Andromeda's satellite galaxies might be remnants of those early galaxies. Fossil fragments from a bygone era. Like ancient stones providing insights into a long-lost civilization. They're like time capsules, aren't they? Containing information about the conditions that prevailed in the early universe. But understanding these satellite galaxies isn't always straightforward. It can be quite challenging, you know? These galaxies are often faint and difficult to observe, and their orbits can be complex and unpredictable. Sometimes it's hard to determine whether a galaxy is truly a satellite of Andromeda, or whether it's simply a chance alignment of two distant galaxies. It's like trying to determine if two fireflies are blinking in synchronicity, or if they're simply flashing randomly, appearing to be connected but not truly linked. It requires careful observation, precise measurements, and a lot of patience. We have to account for the effects of distance, of dust, of intervening galaxies. It's a meticulous, painstaking process. And sometimes, even with all our best efforts, we can't be certain. Isn't that the nature of scientific inquiry, though? To grapple with uncertainty. To acknowledge the limits of our knowledge. To refine our understanding little by little. Andromeda's satellite galaxies, they offer a glimpse into a complex and dynamic universe. They reveal the intricate relationships between galaxies. They tell us about the processes of galactic evolution. They provide clues about the early universe. And they remind us that there's still so much we don't know. So much more to explore. So much more to wonder about. It's a humbling thought, isn't it? To realize how much we still have to learn. But it's also an exciting thought. Because every new discovery brings us a little closer to understanding the grand story of the cosmos. And that's a journey worth taking, isn't it? A slow, gentle, unrushed journey of discovery. A slow, gentle, unrushed journey of discovery. And sometimes that journey leads us to notice patterns, doesn't it? Patterns that emerge from the apparent chaos. Like noticing the way leaves spiral down from a tree, or the way water curls in a stream. These aren't random occurrences, are they? They're reflections of deeper forces at play. And when we look at galaxies, particularly spiral galaxies like our own Milky Way and Andromeda, we see something quite remarkable: spiral arms. Have you ever watched a drop of honey swirl in your tea? It's a mesmerizing sight, isn't it? That slow, graceful rotation, those delicate curves. Spiral arms in galaxies are a bit like that, only on a scale that's almost impossible to truly grasp. Imagine, if you can, a swirling pattern extending tens of thousands of light years across. That's the kind of dimension we're talking about. Now, what exactly are these spiral arms? They aren't solid structures like the arms of a clock. They're more like density waves, ripples in the fabric of the galaxy. Think about a traffic jam. Does that resonate with you? It's not that the cars themselves are inherently different, but rather that they're bunched together in certain areas, creating a slower moving wave. Similarly, in a spiral galaxy, stars and gas clouds aren't rigidly rotating in circular paths. Instead, they pass through these density waves, becoming compressed and concentrated as they do. It's like a river flowing around a large boulder. The water doesn't stick to the boulder, but it gathers and swirls around it. And as these stars and gas clouds pass through the wave, something magical happens. The compression triggers new star formation. Regions of dense gas collapse under their own gravity, igniting nuclear fusion and giving birth to brilliant young stars. That's why spiral arms often appear as bright blue regions within a galaxy. Those are the stars, newly born, shining with a youthful intensity. Isn't it beautiful to consider? Galaxies, like grand cosmic nurseries, constantly giving birth to new stars within these swirling patterns. Now, you might be wondering, how do these spiral arms form in the first place? That's a question that has puzzled astronomers for decades. It's not a simple answer, is it? There are a few different theories, and the truth is likely a combination of factors. One idea is that gravitational instabilities within the galactic disk can trigger the formation of these density waves. Think of a pond. Doesn't the surface sometimes develop ripples, even if you haven't disturbed it? Those ripples are the result of subtle fluctuations, small movements in the water. Similarly, slight variations in the density of a galaxy's disk can grow over time, eventually leading to the formation of spiral arms. Another theory involves interactions with other galaxies. Just as a dancer might spin more gracefully with a partner, a galaxy can be influenced by the gravitational pull of a nearby companion. This interaction can stretch and distort the galactic disk, creating the characteristic spiral shape. And then there's the role of the galaxy's dark matter halo. This invisible, mysterious substance makes up a significant portion of a galaxy's mass, and its gravitational influence can shape the distribution of stars and gas. It's as if there's a hidden hand, gently guiding the dance of the galaxy. The distribution of these spiral arms isn't uniform, is it? In some galaxies, the arms are tightly wound and prominent, like a seashell. In others, they're more loosely defined and fainter, appearing more like suggestions of a spiral shape. And sometimes galaxies have grand design spiral arms, very clearly defined symmetrical structures. These grand design spirals are rarer, and their formation is still not fully understood. It's as though the galaxy is making a deliberate statement, presenting itself with striking clarity. The way these arms are arranged, their tightness, their prominence, it all provides valuable clues about the galaxy's history and evolution. It tells us about the forces that have shaped it, the interactions it has experienced. Consider the patterns on a seashell, for example. They reflect the creature's growth, its environment, its entire life story. Spiral arms are like those patterns, inscribed on the face of a galaxy. And just as the pattern on a seashell is unique, so too is the pattern of each spiral galaxy. No two are exactly alike. Each one tells its own story. Do you find yourself wanting to know the stories? The arrangement of spiral arms also isn't static. They evolve over time, changing their shape and structure in response to various influences. A galaxy might experience a collision with a smaller galaxy, disrupting its spiral arms and triggering a burst of star formation. Or it might slowly accrete gas and dust from its surroundings, gradually altering its overall appearance. Imagine a river, constantly shifting its course, carving new channels, redrawing its map. Galaxies are like that, aren't they? Always changing, always evolving. And as we observe galaxies at different distances from us, we are essentially looking at them at different points in their history. We're seeing a snapshot of their evolution, frozen in time. It's like looking at a series of photographs, each one capturing a slightly different moment in the life of a galaxy. And by studying these snapshots, we can piece together a more complete picture of how galaxies form and evolve. So much depends on perspective, doesn't it? So much can be revealed by simply shifting our viewpoint. Spiral arms, then, are far more than just beautiful patterns. They are windows into the heart of a galaxy. They are clues to understanding its history, its composition, its future. They are a testament to the complexity and wonder of the universe. And as we continue to explore the cosmos, we will undoubtedly uncover even more secrets hidden within these swirling patterns. Isn't that a thought to hold? A universe brimming with secrets, waiting to be unveiled. Isn't that a thought to hold? A universe brimming with secrets, waiting to be unveiled. And those secrets aren't always obvious, are they? Sometimes they're subtly woven into the very fabric of what we observe. Like the gentle curve of a river, it might seem simple on the surface. But look closer, and you'll notice the intricate interplay of currents, the shifting sands, the hidden depths. Galaxies are like that too. Their grand, swirling shapes can be captivating, almost hypnotic. But beneath that beauty lies a fascinating complexity. We've talked about spiral arms, those elegant curves of stars and gas. We've considered how they change over vast stretches of time. And we've thought about how our perspective, our vantage point, shapes our understanding. But there's another crucial element at play, a silent conductor orchestrating the dance of a galaxy. It's not something we might readily see, not with our eyes, even through the most powerful telescope. But its influence is undeniable, pervasive. Imagine a vast, still pond. The surface is calm, serene, reflecting the sky above. But beneath that surface there's a drain, a powerful vortex pulling everything towards its center. You might not see the drain itself, but you'd certainly notice the effect it has on the water. The way it swirls, the way it pulls, the way it shapes the entire pond. That, in a way, is analogous to what we're about to explore. Most galaxies, it turns out, harbor a supermassive black hole at their center. A black hole, as you may recall, is a region of space-time where gravity is so intense that nothing, not even light, can escape. It's a place where the very fabric of reality is warped and distorted. And supermassive means it has a tremendous amount of mass, often millions or even billions of times the mass of our own sun. Think of it as an anchor, not a visible one, but one that holds the galaxy in place. Or perhaps more accurately, not holds it in place, but exerts a profound influence on its shape and behavior. The spiral arms we've been admiring, those breathtaking patterns, are often influenced by the gravity of this central black hole. It isn't a simple direct pull, of course. It's a complex gravitational dance, a subtle shaping force acting over enormous distances. Let's consider the galaxy M31, also known as the Andromeda galaxy. It's our closest large galactic neighbor, a majestic spiral shimmering in the night sky. And at its heart lies a supermassive black hole, which we call M31 Aplaf. Yes, just like people have names, we give names to these celestial objects as well. M31 isn't actively devouring stars at the moment, but it exerts a tremendous gravitational influence nonetheless. It's fascinating to consider that these black holes, these cosmic behemoths, are often quiescent, relatively quiet, yet they are the silent architects of the galaxies they inhabit. They don't always announce their presence with dramatic flares or bursts of energy. Sometimes their influence is felt only through their subtle gravitational effects on the stars and gas swirling around them. Imagine a dancer gracefully gliding across the stage. You might be captivated by their movements, their artistry. But behind the scenes, there's a choreographer guiding their steps, shaping their performance. The supermassive black hole is, in a way, the choreographer of the galactic dance. Now, you might wonder, how do we even know these black holes are there? After all, they're invisible. They don't emit light themselves. How can we detect something that doesn't interact with light? It's a remarkable challenge, isn't it? We rely on a combination of techniques, much like a detective piecing together clues. One method involves observing the motion of stars and gas near the galactic center. If these objects are orbiting something incredibly massive, something we can't directly see, it suggests the presence of a black hole. Think of watching water swirl around an unseen drain. The pattern of the swirl provides a clue to the drain's existence and strength. Another technique involves looking for gravitational lensing. This is where the gravity of a massive object bends the path of light from a more distant object. If a black hole is positioned between us and a faraway galaxy, its gravity can distort the image of that galaxy, revealing its presence. And sometimes, we do witness these black holes actively feeding, accreting matter. As gas and dust spiral into a black hole, they form a superheated disk, emitting intense radiation across the electromagnetic spectrum. This radiation can be detected by telescopes, providing further evidence of the black hole's existence. The properties of M31 have been studied extensively. We know its mass. It's roughly 100 million times the mass of our Sun. We know something about its spin, its rotation, and we're learning more and more about the environment immediately surrounding it. Isn't it amazing that we can discern so much about something so fundamentally invisible? It speaks to the ingenuity of human observation, the power of scientific inquiry. The influence of M31 happens in static. It's dynamic, ever-changing. As the galaxy evolves, so too does the black hole's influence. It's a continuous interplay, a delicate balance. Consider for a moment the implications of all this. Nearly every galaxy we've observed has a supermassive black hole at its core. Does this mean that black holes are somehow fundamental to galaxy formation? Did they come first and galaxies grew around them? Or is it the other way around? These are profound questions, and the answers remain elusive. But the fact that these questions even arise, the fact that we are grappling with these mysteries, is a testament to the incredible journey of human understanding. We're like children exploring a vast enchanted forest. Each discovery reveals new wonders, new puzzles, new paths to explore. And with each step, we deepen our appreciation for the immensity and complexity of the universe. Perhaps the spiral arms are sculpted by the black hole, drawing material inward. Or perhaps the black hole is a consequence of the galaxy's own evolution, a dense remnant left behind by earlier star formation. Or maybe it's a combination of both, a complex interplay of forces that we are only beginning to understand. Think about a river delta, where a river branches into countless streams, depositing sediment and shaping the landscape. The black hole is like the heart of that delta, a central point of convergence and distribution. We are just beginning to unravel the intricate connections between galaxies and the supermassive black holes at their cores. And as we continue to observe and analyze these cosmic systems, we will undoubtedly uncover even more surprising and profound insights. It's a humbling experience, isn't it? To realize how much we still don't know. But it's also a deeply inspiring one, because it reminds us that the universe is full of secrets waiting to be discovered. And it invites us to continue exploring, continue questioning, continue marveling at the wonders that surround us. The more we look, the more we find. It's an endless cycle of discovery. And what a privilege it is to be a part of it. And what a privilege it is to be a part of it. It feels, doesn't it, like we've just been given a glimpse into a vast, swirling dance of creation? We've touched upon the immensity of galaxies, the silent power of black holes, and the hints of connections that ripple through the cosmos. But what if we were to shift our perspective? Just a little. What if we weren't simply looking at a galaxy, but were somehow able to journey within it, to feel the subtle variations in its form? Consider for a moment the feeling of holding a seashell to your ear. Do you hear the ocean? Or perhaps more accurately, do you hear the suggestion of the ocean? It's a sense of vastness, a sense of depth, conveyed through a tiny, delicate form. Galaxies are like that in a way. They appear as flattened disks from our vantage point, a seemingly two-dimensional expanse of stars and gas. But that's just one perspective. Think about a loaf of bread. From far away, it might appear as a flat, rectangular shape. But as you get closer, you notice the subtle curves, the uneven texture, the slight thickness. The galaxy isn't just a thin pancake of stars, is it? It has depth. It has dimension. We've talked about the spiral arms, how they twist and wind like cosmic rivers. We've explored the central black hole, a gravitational anchor in the heart of the galaxy. But what about the thickness of the galactic disk? It's a question that might not immediately spring to mind, but it's crucial for understanding the galaxy's structure and evolution. It's like noticing the thickness of a leaf when you pick it up. It's not just a flat surface, is it? It has a certain depth, a certain volume. And that thickness, that volume, tells a story about how the leaf grew, how it interacted with the sunlight, how it adapted to its environment. The same is true for galaxies. The thickness of Andromeda's disk, for example, varies considerably. It's not uniform. It's not consistent. It's nuanced. Imagine stirring a pot of thick cream. You'll notice that it doesn't swirl evenly. There are thicker regions, thinner regions, areas where it clings to the sides of the pot, and areas where it's more fluid and free. Andromeda's disk is similar. It bulges in some places, thins out in others. Why is that? What shapes this three-dimensional form? One possibility is that the galaxy's rotation plays a key role. As the galaxy spins, centrifugal forces act on the material within the disk. These forces tend to flatten the disk, but they also cause it to bulge outward at its edges, much like the equator of a spinning planet. Think about a ball of clay that you're spinning on a potter's wheel. The faster you spin it, the flatter it becomes. But there's a limit to how flat you can make it. Eventually, it will start to bulge outward, especially at the widest point. Something similar happens with galaxies. Gravity, of course, is constantly pulling the material inward, counteracting the centrifugal forces. It's a constant tug-of-war, a delicate balance between outward expansion and inward collapse. The thickness of the disk reflects this balance, doesn't it? It's a record of the forces that have shaped the galaxy over billions of years. But it's not just rotation, is it? Collisions and mergers with other galaxies can also significantly affect the disk's thickness. Imagine gently dropping pebbles into a still pond. Each pebble creates ripples that spread outward, disturbing the smooth surface of the water. When galaxies collide, they interact gravitationally, disrupting their shapes and structures. These interactions can compress the disk, making it thinner, or they can warp and distort it, creating new bulges and ripples. Andromeda, like all galaxies, has experienced its share of cosmic collisions throughout its history. These events have undoubtedly left their mark on the disk's thickness, adding another layer of complexity to its three-dimensional structure. It's like looking at a landscape that has been sculpted by wind and water over millennia. Each erosion pattern, each ridge and valley tells a story of the forces that have shaped the land. The thickness of Andromeda's disk isn't a simple measurement. It's a window into the galaxy's past, a record of its interactions and its evolution. And as we gather more data, as we develop more sophisticated models, we'll be able to piece together a more complete picture of this intricate structure. But consider this. Even with the most advanced instruments and the most powerful computers, we are still limited by our perspective. We are observing Andromeda from a great distance, looking at it through the veil of intervening dust and gas. We're like trying to understand the texture of a painting by looking at it through a slightly smudged lens. There's always a degree of uncertainty, a degree of approximation. That's okay, isn't it? It's humbling to acknowledge the limits of our knowledge, to recognize that there will always be more to learn. It's in those moments of uncertainty, in those moments of questioning, that we truly deepen our understanding. And perhaps one day we'll be able to journey to Andromeda, to swim within its galactic disk, to feel its three-dimensional form with our own senses. But until then, we have our telescopes, our instruments, and our imaginations. And that in itself is a remarkable privilege. Isn't it? We're trying to map something unimaginably vast, something that exists on a scale that defies our everyday experience. It's like trying to measure the depth of the ocean with a teaspoon. The task seems daunting, almost impossible. But with each observation, with each calculation, with each moment of reflection, we gain a little more insight. We move a little closer to understanding the grand design of the universe. And that's a journey worth taking, isn't it? A journey filled with wonder, with challenge, and with the quiet joy of discovery. So let's consider the nuances of Andromeda's disk thickness. It's not a single number, not a uniform value. It's a distribution, a range, a pattern. And that pattern reflects the complex interplay of forces that have shaped the galaxy over billions of years. It's a reminder that the universe is not static, not unchanging. It's a dynamic, evolving system, constantly transforming and reshaping itself. And we, as observers, as explorers, are privileged to witness this ongoing cosmic drama. It's a humbling thought, isn't it? To realize that we are a small part of something so much larger than ourselves. But it's also an empowering thought, because it reminds us that we have the capacity to understand, to learn, to appreciate the beauty and complexity of the universe. And what a gift that is! What a profound and precious gift. You feel that too? It's a gift to be able to sense that, isn't it? That quiet resonance of connection, of being part of something so vastly grand. It's easy to feel lost in the immensity, isn't it? Like a single grain of sand on an endless beach. But even a grain of sand has its place, its story etched within its layers, and so do we. And so does Andromeda. Consider its disk, the swirling plain of stars and gas that stretches across a space so vast it's almost impossible to truly grasp. We've talked about how its thickness isn't uniform, isn't a simple, tidy number. It ripples, it flares, it tapers. It's like looking at a field of wheat in the breeze. It appears to be a single plane, but upon closer inspection, each stalk moves with its own subtle rhythm, creating a complex, shifting surface. And that complexity, that variation, tells a story. A story of gravitational tugs, of collisions with smaller galaxies, of the slow, inexorable dance of cosmic forces. But how do we begin to tell such a story? How do we begin to measure something so far away, so distant that the light we receive from it has been traveling for millions, even billions of years? It feels almost absurd, doesn't it? Trying to understand something so remote through the faint glimmer of light reaching us across unimaginable distances. It's like trying to understand the taste of a distant fruit based solely on the faint aroma carried on the wind. You might get a sense of it, a hint of its essence, but it's not the same as experiencing it directly. And yet we do it. We strive to measure these distances, to map the universe in 3 dimensions. And the way we do it is through what's known as the distance ladder. It's a rather poetic name, isn't it? A ladder reaching out to the stars. Each rung represents a different method, a different tool for measuring the vast gulfs between us and those distant galaxies. And each rung builds upon the previous one, allowing us to extend our reach further and further into the cosmos. The first rung, the closest rung, involves measuring what we call standard candles. These are objects whose intrinsic brightness, their true luminosity, is known. Think of it like this. Imagine you have 2 light bulbs, one a tiny nightlight and the other a powerful flood lamp. You know how brightly each bulb shines when you're standing right next to them. Now, if you see those same 2 bulbs from a great distance, the further one will appear much dimmer than the closer one, won't it? And by comparing their apparent brightness, you can estimate how far away the dimmer bulb is. It's all about how the brightness we see relates to the actual light it emits. And that's precisely what we do with standard candles. Certain types of stars, like Cepheid variable stars, pulse with a predictable rhythm. The longer the period of their pulsing, the brighter they are. This relationship is well understood, so if we see a Cepheid variable in a distant galaxy, we can measure its pulse period and determine its intrinsic brightness. Then by comparing its intrinsic brightness to its apparent brightness, we can calculate the distance to that galaxy. It's a clever trick, isn't it? Using the stars themselves to measure the distances to the galaxies they reside in. But Cepheid variables aren't visible in galaxies that are incredibly far away. The light is simply too faint. So we need a tool that can reach even further, a brighter standard candle. That's where Type 1a supernovae come in. These are incredibly powerful explosions that occur when a white dwarf star reaches a critical mass. They are extraordinarily bright, so bright that they can be seen across billions of light years. And, crucially, they all have a remarkably consistent intrinsic brightness. Just like the flood lamp in our analogy. So we can use Type 1a supernovae to measure distances to even more distant galaxies. But here's the rub, isn't it? We need to calibrate these standard candles. We need to know, with a high degree of certainty, how bright they truly are. And we do that by using the closer, more easily measured Cepheid variables. We observe a Type 1a supernova in a nearby galaxy where we've already measured the distance using Cepheid variables. We compare its apparent brightness to its intrinsic brightness, as determined by its properties. This tells us how much dimmer it appears than it should, based on its intrinsic brightness. And that dimming is due to the distance and the intervening dust. Then, we can use that information to calibrate Type 1a supernovae in more distant galaxies. It's a delicate process, a careful dance of observation and calculation. Each rung of the ladder depends on the accuracy of the rungs below it. And each measurement carries with it a degree of uncertainty, a margin of error. It's like building a tower of blocks. Each block must be carefully placed, or the whole structure will wobble. And it's humbling, isn't it? To realize that our understanding of the universe is built upon these layers of assumptions and approximations. We're constantly refining our methods, improving our measurements, striving to reduce those uncertainties. And as we do so, our picture of the universe becomes sharper, more detailed, more profound. But what about galaxies even further away than those where we can observe Type 1a supernovae? What then? Well, there's another rung on the ladder, a rung that relies on a different type of standard candle, a different trick of the light. It involves something called Tully-Fisher relation. This relation connects a spiral galaxy's rotation speed to its luminosity. Faster rotation means brighter galaxy, a pattern that's been observed and confirmed. Again, knowing a galaxy's intrinsic luminosity from its rotation speed, we can estimate its distance by comparing the apparent brightness. It's a more indirect method, not as precise as using Cepheids or Type 1a supernovae, but it extends our reach even further. So the ladder continues, each rung representing a different technique, a different way of probing the vast distances of the universe. Each rung building upon the previous ones, allowing us to glimpse ever more distant galaxies, ever more remote corners of the cosmos. With each measurement, with each calculation, we deepen our understanding of the universe and our place within it. It's a continuous process, a journey without end. And what a privilege it is to be a part of it, isn't it? To be able to ponder these vast distances. To marvel at the ingenuity of the methods used to measure them. To feel a sense of connection to the cosmos. It's a humbling experience. A profoundly moving experience. Does that resonate with you? It's a humbling experience, a profoundly moving experience. Doesn't it feel like standing on a shore, watching waves roll in, each one carrying a tiny bit of a distant ocean to your feet? Each measurement, each calculation, isn't just a number. It's a whisper from a faraway place, a story told across light years. And these whispers, these stories, they allow us to begin to understand not just how far things are, but also when they came to be. Think about it for a moment. We've been looking at galaxies, increasingly distant, using ever more ingenious methods to figure out how far away they are. But distance isn't just about space. It's inextricably linked to time. Light takes time to travel, doesn't it? The farther away a galaxy is, the further back in time we are looking. We are seeing it as it was, not as it is at this very moment. And so, understanding the age of a galaxy isn't simply a matter of looking at its current state. It's about piecing together a history, a timeline, based on what we observe now, knowing that we're looking at a younger version of itself. And when we consider galaxies like Andromeda, our galactic neighbor, the questions become even more intricate. Andromeda, isn't it remarkable to think of it as a neighbor at all? When you look up at the night sky, it appears as a faint smudge, a hazy patch of light. You might not even notice it, unless you know exactly where to look. But that faint smudge? That's an entire galaxy, containing billions upon billions of stars, a cosmic island teeming with life, perhaps. And it's approaching us slowly but surely, drawn together by the relentless pull of gravity. It's a dance that has been unfolding for billions of years, and will continue for billions more. So let's consider Andromeda's age, its formation, and its evolution. Just as with the distance ladder, unraveling the story of a galaxy's age is a layered process. We can't simply glance at it and say, it's this old. Instead, we must consider several lines of evidence, different clues that help us build a picture of its past. One of the first things we look at is the types of stars we see within Andromeda. Different kinds of stars live different lengths of time. Massive, brilliant stars burn through their fuel quickly and have relatively short lives, perhaps only a few million years. Smaller, less luminous stars, like our own Sun, live much longer, potentially billions of years. By studying the distribution of stars of different ages within Andromeda, we can gain insights into its star formation history. If we see mostly young blue stars, it suggests a recent burst of star formation. If we see a mix of young and old stars, it indicates a more continuous, albeit perhaps uneven, process of star birth. It's like looking at a forest, isn't it? You see towering, mature trees standing alongside saplings just beginning to reach for the sky. The proportions of each tell you something about the forest's history. How often have new trees been planted? How long have the old ones been standing? And that's essentially what we're doing when we examine the star populations of Andromeda. But the story doesn't end with the stars themselves. We also need to consider the gas and dust that make up Andromeda. These materials are the raw ingredients from which stars are born. The amount and distribution of gas and dust within a galaxy can tell us a lot about its star formation potential and its overall evolution. Furthermore, the chemical composition of the gas and dust can provide clues about the galaxy's past. Elements heavier than hydrogen and helium, what we call metals in astronomical terms, are created within stars and released back into the interstellar medium through stellar winds and supernova explosions. The abundance of these metals increases over time as successive generations of stars are born and die. By measuring the metallity of Andromeda's gas and dust, we can estimate how many generations of stars have lived and died within the galaxy. It's like examining layers of sediment in a riverbed, isn't it? Each layer represents a different period in the river's history. And the composition of the sediment tells us something about the environment at that time. Similarly, the chemical composition of a galaxy's gas and dust tells us something about its star formation history. And then there's the galaxy's structure itself. Andromeda is a spiral galaxy, like our own Milky Way. Spiral galaxies are characterized by their flattened disk shape and their prominent spiral arms. These spiral arms are regions of enhanced star formation, where gas and dust are compressed and triggered to collapse into new stars. The shape and structure of a spiral galaxy can be influenced by a variety of factors, including interactions with other galaxies and the distribution of dark matter. By studying Andromeda's structure, we can learn about the processes that have shaped it over time. Think about a river flowing through a landscape, doesn't it? The river's path is influenced by the terrain, carving out valleys and shaping the surrounding land. Similarly, a galaxy's structure is influenced by the gravitational forces acting upon it. All of these pieces of information, the ages of the stars, the composition of the gas and dust, the shape and structure of the galaxy, contribute to a more complete understanding of Andromeda's age and evolution. And the more we learn, the more complex the picture becomes. It's not a simple linear story. It's a tapestry woven from countless threads, each representing a different aspect of the galaxy's past. Andromeda is estimated to be around 10 billion years old. That's an almost incomprehensible length of time, isn't it? Our own solar system, our Earth, our very existence, is but a fleeting moment in comparison. And yet, within that 10 billion years, Andromeda has undergone a dramatic transformation. It has grown from a smaller, less organized collection of gas and dust into the majestic spiral galaxy we see today. It has experienced periods of intense star formation, followed by periods of relative quiescence. It has interacted with other galaxies, merging some and cannibalizing others. And it has continued to evolve, driven by the relentless forces of gravity and the ongoing cycle of star birth and death. It's a process that continues even now. Andromeda is still forming new stars, still accreting gas and dust. It's a living, breathing entity, constantly changing, constantly evolving. And it's all happening on a scale that is almost beyond our comprehension. Doesn't that leave you with a sense of awe, a sense of wonder? And as Andromeda continues its journey through the cosmos, it's on a collision course with our own Milky Way galaxy. Billions of years from now, these two majestic spirals will merge, colliding and intertwining to form a new, larger galaxy. A cosmic dance of epic proportions. It's a sobering thought, isn't it? A reminder of the vastness of time and the scale of the universe. It's also a reminder that even the most permanent seeming structures in the cosmos are ultimately subject to change. Nothing lasts forever. Everything is in flux. And yet, even as galaxies collide and stars are born and die, the universe continues to unfold, revealing its secrets to those who are willing to look and to ponder and to marvel. It's a privilege, isn't it?